Okay, so let's go ahead with the lecture. We are going to continue the discussion on the turbojet analysis. So we have seen the we are by now you should be able to analyze the inlet. You should be able to analyze compressor, burner, and turbine and the nozzle separately. But now we want to combine them all together. So essentially analyze the whole engine. So we want to, and eventually your final goal in analyzing the whole engine is to calculate, not the final goal, but the final step of this analysis is going to be to calculate the engine thermal efficiency of the engine, or to use the efficiency that is given to you and calculate something else, or like the exit velocity or whatever. Okay. I'm sorry, I did something here that I shouldn't have. What is going on? That's all right. Okay, so let's talk about the ideal turbojet engine. As we have mentioned before, the ideal turbojet engine, which has the components of inlet, gas generator, and the nozzle, and the gas generator included the compressor, combustor, and the turbine, is essentially just an ideal Brayton cycle. And the thermal efficiency of an ideal Brayton cycle is going to be 1 minus T naught over T3. So the thermal efficiency is going to be 1 minus the ratio of T at the station 0, which is your ambient emission, and the ratio of T3, which is going to be, what is the station 3? What the stage of engine is a station 3? Burner intake, or the compressor exit, right? So at this point, we are dealing with the compressed gas. You can, of course, play with this a little bit. You can convert them to the total temperatures by just multiplying by T2 and T3, right? And we have already seen the definitions. This is going to give you the compressor temperature ratio, and this is going to be your tau R, T2 over T naught, right? And we can essentially replace tau of C with pi of C, because there was supposed to be this relationship between the two, and then tau of R is going to be equal to, is essentially the temperature ratio between the inlet and the ambient temperature, which is the ambient total temperature itself, with the ratio of the static temperature. So we can replace that with 1 plus gamma minus 1 over 2 m naught squared, the ambient Mach number, the flight velocity. Okay. But then the question is, what would be the maximum thermal efficiency you can get out of a cycle in general? What's that? 1? No, you definitely cannot get to 100%, right? And you have seen, hopefully you have had this discussion in your thermodynamics, right? I know you have, because you have already talked about it. What is the maximum efficiency you can get out of a cycle? Or what is the most efficient, theoretically most efficient cycle? Carnot cycle, yeah. Don't doubt yourself. Yeah, the Carnot cycle, for which the TS diagram is just this, right? So the maximum thermal efficiency of a Carnot cycle, this is station 4, this is station 0, is going to be 1 minus T0 or T naught over T4. So what does it mean? That's essentially going to mean that the maximum efficiency you can get out of a turbojet engine is going to be equal to the efficiency of a Carnot cycle. which means that to get the maximum efficiency of your Brayton cycle or the turbojet engine, you want to increase the station 3's temperature as much as possible, and you want to bring it closer to T4. Right? Does that make sense? Right? Because the maximum efficiency you're going to get is the Carnot cycle's efficiency, which is 1 minus T naught over T4. But our efficiency is calculated by 1 minus T naught over T3. So the goal should be to increase the T3 as much as possible and take it closer to T4, right? Which means that this ratio is going to be smaller. T naught over T3 is going to be smaller, and 1 minus T naught over T3 is going to be larger. Okay, so what does it mean for our TS diagram? So 0 to 3 is essentially your ambient to the compressor, then 3 to 4 is your burner, right? Then 4 to 9 is your is your essentially combines your turbine and the exhaust nozzle, right? What does it mean for this diagram when we say we want to increase T3, or we should increase T3 as much as possible if we want to increase the thermal efficiency? It essentially means that the difference between T3 and T4 is going to be smaller, so you're going to move in the direction of increasing cycle pressure ratio, which means that your T3 is going to end up being higher and higher, and these two stages, the stage 3 and 4, is going to become closer and closer. Does it make sense? So, from an entropy perspective, your stage 4 is going to have lower and lower entropy. That's the ideal case, right? But that's not what happens in general. That's the ideal case is, I mean, that should happen in general if you increase the temperature after the compressor, right? But the ideal case is going to be that. And we can say your thermal efficiency related to the pressure ratio and the ambient Mach number. We can just repeat the equation here. I thought thermal is 1 minus 1 over the pressure ratio is over gamma minus 1 over gamma, multiplied by 1 plus gamma minus 1 over 2 and not squared. Okay. But then the question is this a good thing?
You mean raising T3? Is that what you're saying?
I mean, it will definitely increase the efficiency. But what is what are the cons of this increase in efficiency? Okay, how? Let me actually mention this before talking about that. So the maximum compressor pressure ratio, you can get out of that. Most likely the theoretical value is around 40 to 45, and there's always relating to the discharge temperature. There is always a technology limit, right, for the temperature. So there is a limit you cannot go further, and that dictates your maximum compressor ratio. But yeah, you were saying.
Isn't like regular total entropy change lower, so you could get like less energy? There'd be less of a change in it?
Less of a change in energy. So okay, we are getting somewhere, guys. So what Joshua said is that we are going. What did you say?
I said that as increased T3, like in comparison to before, you'll have all the power, like power output.
So you're going to have a total lower power output, right? And since I assume you agree with it, and Tyler explained what's going to happen to get the lower power output. But I want to get all of your contributions. What all of you guys think.
It just seems like you wouldn't have as much power because the whole point of the combustion stage is to increase the heat, which would increase like the speed of the gases. And if they're going in at relatively the same temperature they're going out, I feel like it's going to drastically decrease power.
Okay, so what you're saying is that you're putting in less power, right? Because the temperature change between the in the combustor is going to be smaller. Okay, it's essentially is the same thing as the third.
The other thing I'm thinking about is honestly, I guess it's really simple, but the graph on the right, you have a technology limit, right? So if your temperature in your T3 is too high, essentially your compressor, wouldn't that lead to like, I don't know, higher fatigue or something like that in your engine?
That's a very interesting concern, and that is definitely correct. But we are dealing with the ideal cycle here, right? So you're talking about the ideal Brayton cycle, right? Do you have anything else to add? Yeah.
You want more combustion, you want a greater temperature change. That's pretty better.
Okay, so you agree with the others, essentially.
Yeah, if there's a greater temperature change, there's more combustion means more thrust.
Okay. Okay. So yeah. So we heard all your opinions. We'll talk about it. Before moving on, I should have mentioned this before. Keep in mind that engine components are not ideal in general case. So the ideal case usually never happens. And then the next thing we want to talk about after the discussion just had is about high Mach numbers. We have already heard that in the high Mach numbers, you won't need a compressor. And we will see the discussion on that as well later on. Okay. So let's actually, instead of comparing the combustor stage, let's compare the compressor and the turbine stage, right? The total work output of your system is essentially going to be the total work energy you are putting in the gas, essentially, is going to be the energy exchange in the turbine minus the whatever energy you have lost in the compressor, right? So HT4 minus H9 minus the HT3, which is the combustor exit, minus the ambient enthalpy. Okay? Which essentially is the difference between the expansion leg and the compression leg of the engine, of the turbojet engine. Or we can say this is the difference between the power production and the consumption. Okay. You can actually play with the equation a little bit. You can take the HT4 out, and then you can replace the enthalpy ratios with CPTs, right? CP for stage 9 and 4 is the same. CP for stage 9 and 3 is the same. So you're going to get pressure ratios. And we also have we can replace these with isentropic relationships, where we can relate the whole work to the pressure ratios as well, right? Is there any questions up until this stage? So instead of looking at it, you guys in your explanations of why increasing the T3 is not the best case scenario for our engine design. You talked about the compressor, the energy input in a compressor, in a combustor, right? So, but I'm having or your book is having a different perspective. Your book is looking at the work output, right? I assume you can get to the same conclusion as the book has, going from that perspective. But I haven't gone from that perspective. Okay, so let's do the simplifications. Eventually, you can find that your pressure, your total work of the turbojet engine using this equation, which relates your work to all of these enthalpies and the temperature ratios. And just a reminder, T lambda is HT4 over H naught. TR is HT naught over is T naught TT naught over T naught, which is equals to 1 plus gamma minus 1 2m squared. And TC is your compressor temperature ratio, which is the temperature ratio. But one other design parameter, or one other thing that you would desire from your engine design would be to increase this work here, right? Yes? You want to increase the work that you're putting into your gas, essentially. How can we find the maximum work that we can put in a gas? We have the equation for it. You want to find the maximum value of this. How can we find the maximum value? That's it, right? Some questions only have very simple answers. So you want to take the derivative with respect to WC over H naught, and that derivative must be equal to 0. But you're taking the derivative with respect to TR and TC, which are essentially TR multiplied by TC, which are essentially the things that you can play with, right? You cannot play with the temperature after the combustor because that's your temperature limit, right? So if you take the derivative and set it equal to 0, this is going to be your final relationship, right? If you take the derivative with respect to dTr dC from this equation, what you are going to get is going to be 0 minus plus 1 over tau r tau c to the power 2 minus 1 plus 0, right? Very simple derivative, you take that, and you take 1 to the other side, you're going to get T lambda over tau r tau c to the square equals to 1. Play with that a little bit. Tau r multiplied by tau c is going to be a square root of tau lambda. So to get the maximum work, the maximum specific work out of your cycle, this relationship must always hold true. Tau r multiplied by tau c is must be equal to the square root of tau lambda, which means that your tau c must be always equal to the square root of tau lambda over tau r, and then we can replace that as well. We can replace tau r with the relationship we already have. That's the ratio between the total condition and the stagnation and static condition, right? Tau r 1 plus gamma minus 1 over 2. The same equations here. Okay. So how can we relate tau c to pi c, the pressure ratio? We already have that relationship, don't we? So go back to your notes, and find the relationship between the pressure ratio of a compressor and the temperature ratio of a compressor.
So tau C plus minus to the power of gamma minus 1.
That's it. Yeah, exactly. So essentially, if you take this equation to the power gamma over gamma minus 1, right, which is has to be reversed, right, you are going to get the optimum pressure ratio to have the maximum thrust or the maximum work output. Okay, so this analysis here tells us that there is an optimum pressure ratio, right? If we go back to the TS diagram here, which you have here, the idea is if you increase the cycle pressure ratio, you are going to have a TT3 that is closer to T34, which means that you are going to increase the efficiency. But our discussion over there told us that there is an optimal value for this pressure ratio, right? If you go further from that, you're going to increase the efficiency, but at the cost of reducing thrust, which is the efficiency is not the main goal. Always the thrust is the main goal of the turbojet, right? You want to have thrust, right? So that's very important to keep in mind that there always should be a balance, and we will talk about where that balance should be in a little bit. So we have the optimum pressure ratio, okay? But then the question is, what is the maximum? Can we actually find the maximum flight Mach number which renders the compressor in an aircraft engine useless? Anyone? No, it is very close to Mach 3 as we had it as slide, but
How do you define an efficiency of 0 or
that's my question. So what should happen to a compressor that makes it useless? What is the main job of a compressor? Compressing there. So
Like to the pressure ratio.
what should happen to the pressure ratio, right? It should be 1, exactly. So it means that your compressor is not compressing air, right? So it's a useless thing that is there. So
I mean, if it's just a little bit greater than 1, isn't that still kind of useless? And why build all that stuff? It's not going to do it. There's got to be a limit.
the limit is 1. The limit is definitely 1.
What's the design limit?
So that's a very good question. So the design limit, we will talk about the design limits in general. We will talk about the correction factors a little bit in general. But think about it this way. You're flying an aircraft, right? Can you ever start flying at Mach 2? Can you?
If you get dropped from another plane or something.
But that's not the start flying. And you already have a flight velocity, right? Your engine may be off, but your aircraft is flying, right? So you cannot ever start flying from Mach 2, Mach 3, right? So you are always starting from Mach 0. Does it make sense? Okay, so you always, when starting the flight, you always have some sort of, you have to have some sort of, not something, you have to have a compressor, right? There's no other option, right? And then when, pardon me?
I said or rocket.
That's a whole different thing, right? That's a whole different concept. Yeah, but But when you get to Mach 2, Mach 3, what's happening is that your aircraft is already flying, right? And even if you turn off the compressor or change the engine to a ramjet, right? Your performance may take a hit because you have removed the compressor from the equation, which means that you are essentially the pressure you're giving to the turbine is not as compressed as it should be, right? It's a little less compressed. Your performance may take a hit. You're going to have a smaller thrust, but it's not going to change the flight, right? So that the parameter that you're going to have is pressure ratio of 1, right? As you get closer to it, you can just turn off the compressor. Or, I mean, there are mechanisms that change from the non-ramjet to ramjet, right? You can do it at 0.9. You can do it at 0.8. The only difference is going to be that you are not going to have going into the combustor, you're not going to have the necessary pressure. Does it make sense? What does it mean? It means that your turbojet is not going to run, or your jet is not going to run as an ideal case, which already is not happening. Does it make sense? Okay, so that doesn't really, that's not an important parameter. I don't want to say that's not an important parameter, but we'll get there. Hopefully, if you have enough time. Okay, so essentially, for the theoretical value for rendering the compressor useless, right? Because we are dealing in theory at this stage, the phi of C must be equal to 1, right? Which you just plug that in. It's going to be the maximum Mach number you're gonna get with the compressor in place. The maximum Mach number at which you will need a compressor. You can actually plot this, plot the optimum compressor ratio versus the plot Mach number for different tau lambdas. So you can see it looks like an asymptote, right? It converges. But where you put that design criteria is something that hopefully we'll get to talk about later. Okay. So let's go back to the discussion we had at the beginning. The idea was you want to have an optimum pressure ratio that will give you a specific thermal efficiency. Okay? So you cannot have both a maximum efficiency and a maximum thrust, right? That's not going to happen. There is always a compromise between the two. So you have to make a compromise, right? You have to have you have to find an optimal solution. So for example, if you look at these three plots, which one will give you the highest efficiency? B, because it has a higher T3, right? Or the difference between T0 and T3 is much higher, right? So that ratio T0 over T3 is going to be much higher. Well, which one is going to be the maximum? Is going to give you the maximum work bill. The one that has the maximum area, right? Does it make sense? I mean, you already know that. Okay, so we want to get somewhere with this discussion. We have already discussed most of these parts. You can replace the taus with their temperature counterparts. And so let's do it, right? So our tau C is Tt0 over T0 multiplied by T3 divided by Tt2, right? Tt2 and Tt0 are equal together, so it's essentially going to be Tt3 over Tt0. Does it make sense? Okay. So what you're saying with this equation is that Tt3 over Tt naught is equal to Tt4 over Tt naught. Okay? And before that, just to recap, just to make sure we need to know what does this equation mean? When did this happen?
The maximum work.
The maximum thrust, exactly. So we're going to find the maximum, the condition that's going to give us the maximum work, right? We already know how to find that optimum pressure ratio, but we want to find the condition in our CS diagram that will give you the maximum. We already know that for efficiency, you want to get as close as possible to Tt4, right? So we essentially are replacing this here, and we are replacing T tau lambda with this definition. You can multiply it by T9 and divide by T9, essentially nothing, right? And then you can replace Tt4 with Tt3. And what's going to happen here is that on the numerator, you're going to have the square root of Tt3 over Tt9. And on the denominator, you're going to have just the square root of T9 squared to the power 2. Okay? So essentially, your equation, this equation is going to become this. Tt3 over T naught is equals to a square root of Tt3 T naught over T3, T9 over T3. Does this make sense? Is there any confusions here? Did you follow? Okay. So can we make any conclusion from this equation? Can we simplify this further? Of course, T naughts will cancel out, so you're going to get Tt3 equals to the square root of Tt3 T9. What does this mean?
So Tt3 squared would be equal to Tt3 times T9. So Tt3. So they're essentially.
Exactly. That's the idea. So essentially, to get the maximum work output, your Tt3 must be equal to T9. What does it mean for the TS diagram? For the TS diagram. What does this mean for the TS diagram? It means that to get the maximum area, essentially, of a TS diagram, an ideal TS Brighton cycle, station 3 and station 9 must have the same temperature. That's the idea. Is this going to give you the maximum efficiency, though? No. But it is going to give us the maximum work, right? Okay. And so essentially, you just have to know that there's always a compromise somewhere, right? And I also want to remind you that we define the thermal efficiency of a turbojet engine as the amount of the heat changes in kinetic energy divided by the total input heat, essentially, and that F multiplied by QR. Okay, which is essentially the same thing as 1 minus T naught over T3, right? Which is essentially, if you just do the math, do the analysis, you will definitely get to 1 minus T naught over T3, which was the definition of the efficiency of the Brighton cycle. So the our older definition of the thermal efficiency of the cycle is essentially the same as the thermal efficiency of the Brighton cycle. Is there any questions here? No? Okay. So let's move on. Let's talk about the propulsive efficiency of the turbojet engine. Does anyone remember how we define the propulsive efficiency?
Equation or
No, what was, like, not the equation, what was the concept? Just think about it. You don't need to go back to your notes. Just think about it, right? The thermal efficiency was how much we can, how much heat, how much work we can extract from the input heat, right? Which is always the definition of efficiency, how much you can extract from what you're given. That's the idea, right? So based on that, how would you define the propulsive efficiency? Let's talk about the final goal of the turbojet engine. Right? What is the final goal of the turbojet engine? Thrust, right? And what are we given? What is the given part? What is the input part of here? We are given the energy increase, right? The kinetic energy increase. So essentially, how much thrust you can extract from a given energy jump, right? Of course, thrust is a force, and energy is energy. They have different units. So we are going to use F dot B. Momentum. So we define the propulsive efficiency as F dot V naught, which is your flight velocity, divided by the changes in the kinetic energy. Of course, the uninstalled thrust, we know we can find the uninstalled thrust using the m.9 V9 minus m.0 V0 plus delta P0 minus P9 minus P0 A9. Okay, and for a perfectly expanded nozzle, you're only gonna get m.0 V0 minus V9 minus V0, and eta of P for a perfectly, or a propulsive efficiency for a perfectly expanded nozzle is going to be T2 divided by 1 plus V9 minus V0, which is something we have already discussed. So this shouldn't be anything new to you guys. And the velocity ratio, we can see the relationship between the velocity ratio and the propulsive efficiency here with this plot. As you increase the velocity ratio, your propulsive efficiency is going to decrease. Okay. Let's talk about it a little bit. Let me ask you this question. So, I remember we have talked about this. The idea was, if you increase the velocity at the exit, you are going to get more thrust. That is the idea, right? And my answer was, it's a little more complicated. So, based on the discussion we have had here, is there anyone who can tell me what is the complex part of that? Because the equation of the thrust is telling you V9 minus V0, right? Higher V9, higher thrust. Are we clear on what the question is? Okay.
So you're saying that, so what you just said was higher V9 is as the initial velocity increases, your propulsive efficiency decreases. So at some point there's going to be like an inflection point of you have
As the initial velocity increases, your propulsive efficiency decreases.
Yeah, as your V9 increases, your propulsive efficiency decreases.
Okay. That's actually the complicated part, right? That's the complicated. So you are essentially increasing thrust. That's of course what's happening, but at a very huge cost, right? You're essentially your gradient energy jump is going to be much higher, and the amount of gradient energy that is going to be transformed to thrust is going to decrease as you increase V9. So you're going to have a lot more losses as you increase the exit velocity. Does that make sense? Okay. So, but how can we calculate the overall efficiency of a turbojet engine? Very simple. Just multiply the two efficiencies, the propulsive and the thermal efficiency. You're going to get F multiplied by V naught divided by your total heat input, which is m dot F Q R. We can, of course, play with this a little bit. We can divide everything by m dot naught, which is your mass flow rate of air. In the numerator, you're going to get F divided by m dot naught multiplied by V naught. And what does this stand for? What is F divided by m dot naught? It is the specific thrust, exactly. And in the denominator, you are going to get F, which is fuel to air ratio, which essentially is a fraction of thermal power invested in the engine by the fuel. And it's converted to thrust power. Okay. But how should we solve the problems? What are the different steps? Or what is the final goal you want to do, right? What is the final thing you want to calculate? There are essentially three main things that you want to calculate when solving a problem or when analyzing a jet engine in general, right? You want to find the specific thrust, which is F divided by m dot naught. You want to find the thrust specific fuel consumption or the specific impulse. And you want to calculate all the efficiencies, right? Thermal, propulsive, and overall efficiency. Let's talk about the number 2 here, the thrust specific fuel consumption or a specific impulse. How can we determine which one should we go with? Should be like there are, as I said, there are three main things you want to calculate, or three main steps that you want to, three main parameters that you want to calculate, right? You have the overall efficiency, the specific thrust, and CSFC or IOS. The question I have for you is that how can we determine whether we want to calculate TSFC or IOS? And we have talked about this. So that was a heavy breathe. You didn't like the question? Let's actually go and start with you.
I'm probably wrong, but I want to say that we looked at specific impulse when we were talking about like rocket engines, and we were talking about thrust specific fuel consumption. We were talking about like jet engines and compressors.
I would say you are wrong. You're correct in that, but you are on the correct path, right? And that's all we need. I want you to be on the correct path, right? So just think about it. Don't go back to your notes. Don't go back to your notes. So when we are talking about the specific fuel consumption, right? We are talking about the standardized amount of fuel that you need to consume to generate thrust, right? When we are talking about the specific impulse, what are we talking about? The amount of energy you can essentially get out of that field, right? So essentially, to understand which one you need to calculate, you need to see which one is the biggest priority for you. TSFC talks about your fuel efficiency, right? Impulse talks about the maximum amount of energy you can get. So fuel efficiency is more important for what? For what kind of applications? For the commercial airlines, right? You want to bring the cost down as much as possible. Or you want to be environmentally friendly. But I would assume most businesses don't even care about that. They want to just bring the cost down. And but what about a specific impulse then? That's it, right? You want to have as much power as possible. You know, you don't really care. That's actually the not caring about the amount of fuel that you are going to consume will lead to the use of afterburners as well, which will be the topic of discussion shortly, hopefully, if you have the time. If not, then on Wednesday. So how should we solve these problems? These type of problems, we want to start by finding the fuel to air ratio and also the exhaust velocity. And then when you find the fuel to air ratio and the exhaust velocity, you can find the specific thrust. If you plug in the equation for the thrust and you just divide it by m dot naught, this will be the equation, the main equation you're gonna have for thrust. You can keep in mind that we can write the m dot naught as a function of your exit mass flow rate over 1 plus the fuel to air ratio, and then your exit mass flow rate, your exhaust mass flow rate is equal to the density at the exhaust, the area of the exhaust and velocity of the exhaust. So essentially we are going to relate, the goal here is to relate this specific impulse to V0 completely and remove the need for the end dots, right? And then this density, we can use the ideal gas law to transform into pressure, right? Pressure and temperature. So your end dot naught is going to be equal to T9, A9, B9 over RT9 plus multiplied by 1 plus F. So you plug that in, the equation, you substitute that whole equation with n dot, you will substitute n dot with that whole equation, and this is what you are going to get. You can play with this a little bit. You can rearrange and simplify, and you'll eventually get to this equation. Fn over n dot naught is 1 plus F multiplied by V9 minus V0 plus RT9 multiplied by 1 plus F over V9 multiplied by 1 minus the pressure ratio. So here we don't have the m dot anymore, it's just f dot f, and your specific thrust is going to be only a function of velocities, pressure, and temperature. Okay. Can we simplify this even further?
Perfectly expanded.
No, without making any physical assumption, just with playing with the numbers, with the equations and the parameters you have. Just think about it. What is RT9 multiplied by 1? What can we do with RT9?
I don't even know if this is called for teacher related to sound.
Exactly. Thank you. Thank you. That was a very good out of the box thinking. Exactly. So we we know that the speed of sound is at station 9 is gamma, square root of gamma RT9, right? So essentially RT9 is going to be equal to A9 squared, A9 to the power 2, divided by gamma. You plug that in the equation you have here, right? I mean, you don't need to do this. Just if you do the simplification, if you do the plug in the equation, you are going to get to this equation: 1 plus f multiplied by v9 multiplied by 1 plus 1 over gamma m9 squared multiplied by 1 minus p naught over p9 minus v naught. Okay, so essentially, eventually, we can find the specific impulse as a function of velocity, pressure ratio, and the Mach number. That's it. And especially TSFC is defined as m dot f over fn. We can divide everything by m dot o, which is going to be f divided by fn over n dot naught. So your TSFC is essentially equals to your Q to air ratio divided by a specific thrust. And if you recall from the previous slides, we know that the overall efficiency is somehow related to 1 over TSFC. Is there any questions here? No? Okay. So the next topic is going to just talking about the afterburners. But before moving on, I want to make sure we are clear on what to do when dealing with this type of problem, right? We want to use a technique called the marching technique. This essentially means that you start on station 0, you do the calculation, whatever you need to calculate, you calculate whatever you can calculate. Essentially, if you are given the pressure ratio, you calculate the temperature ratio. If you are given the efficiency, you use that to calculate whatever you can calculate. And you will have a complete, like you have all the numbers you can have for each station, then you move on to the other, right? And you move forward. Then you eventually end up calculating the thrust and the specific thrust and TSFC and all the efficiency, right? So that I assume that understanding and comprehending the technique is very simple, but there are a lot of calculations, there are a lot of like divisions, multiplications. You just have to make sure that you are careful in making all of those calculations, right? You don't want to end up with a very wrong one, because if you make one mistake at the beginning, then everything is going to be messed up, right? Does that make sense? Okay, so let's move on. Yeah, this is not supposed to be here. But before talking about the afterburners, let's take a look at the regular turbojets. A schematic of the regular turbojet. You have the airflow coming in, you have the inlet part, you have the compressor, burner, turbine, and the exhaust part. And the TS diagram for this essentially looks like this, right? We go from station 0 to T3. This is not an ideal TS diagram anymore, right? We have the entropy increase at every stage, right? And depending on your nozzle condition, you can have an expanded nozzle, or under expanded nozzle, over expanded nozzle, or perfectly expanded nozzle, right? But what's going to happen to your engine when you add an afterburner? So that is going to be the topic of discussion. An afterburner is essentially a a huge section of the jet that comes after the turbine. Right? What are we going to do in an afterburner is that we are going to add some fuel to the stream again, and then have some sort of explosion. Like I ignite the fuel, ignite the mixture, and get more thrust out of it. Okay. It usually contains two specific parts. The first part is just the afterburner itself, which we will discuss later. Another part is a convergent divergent nozzle. So in an engine without an afterburner, you usually don't have a convergent divergent nozzle. You have a regular nozzle, right? But with an afterburner, you definitely need to have a convergent divergent nozzle. Afterburners are mostly used in military applications, mainly because they can actually double the thrust you can get out of the engine, but they will quadruple the amount of fuel you are going to consume. So the fuel consumption is very, very high with the afterburner. Of course, there are ways that you can like minimize the fuel consumption, but from fuel consumption standpoint, using an afterburner is not worth it. I mean, yeah, just from that fuel consumption perspective. Okay, so what does it mean for that convergent divergent nozzle? Think about it this way. Your afterburner is not always on. Afterburner is something you can turn on and turn off, and sometimes you need it to be turned off, right?
So it must be adjustable.
Just need the convergent divergent nozzle area must be adjustable, which means that the choking area, the throat area, essentially, which you always design to have a choking condition, must be a variable area. But how can we design that variable area, right? How should it adjust itself? If you write the continuity equation, your continuity equation is going to look like this between the station 7 and 8, or I mean, you can actually calculate your m dot at the station 8. That's right. You're talking about this one. At the station 8, using this equation. This equation was derived based on the conservation of mass equation, right? And we are not going to go over the proof, but
Was that the bonus point?
yeah, but we are not going to go over the proof here, right?
It's annoying.
Annoying?
Yeah.
Why?
There's a lot of math.
Oh, a lot of math. Mathematics is not annoying.
No.
I'm just missing it. Don't worry about it. So m dot is let's continue. And we are a little behind the schedule I had in mind. But m dot is a square root of gamma over r et over square root of t a m, and multiplied by 1 over 1 plus gamma minus 1 over 2 m squared. You have the equation with it, right? You don't need me to read through it, right? But the question you have is that you want to answer is that which part of this is the main variable other than the area. We know we have to change the area to keep the m dot constant, right? Or to better ask the question, which part of this is the main variable as far as turning on and off the afterburner is concerned?
So the m dot has to stay constant if the afterburner is on or off. So that's what we're trying
That's the idea, because you want to, yeah, exactly. At the throat, you want to get the choking condition. So what is the main parameter? Okay, we are actually creating an explosion, an extra explosion. So which parameter should be of concern here? Should be the main focus here. Temperature, right? That's usually the case with ignitions, right? In general. So you can actually prove that all of the other parameters should remain fairly close to each other or even constant. So your area ratio with afterburner on and with it off is going to be related to the square root of temperature at that station, the total temperature at that station, with having the square root of the total temperature with having the afterburner on or off. Okay. But what is going to be added? Which stations are going to be added to our analysis? What are the parameters we need to focus on? What do we have to calculate, right? When you include an afterburner. So the afterburner, as you can see, is usually composed of an inlet diffuser, the same as a combustor, right? Why do we have an inlet diffuser? Is there anyone who can tell me why an afterburner or a compressor should have an inlet diffuser? Why would you want to increase the pressure?
Wouldn't that also increase the density of the gas? Make it easier to ignite?
Okay, so easier to ignite. Let me ask you this question. Let me ask you something. What was an ideal combustion? What was the main characteristics of an ideal combustion? You remember we had this discussion when we talked about combustion? It happens slowly, right? So deceleration is very important here, right? You wanna make that as slow as possible to get closer to that ideal combustion, right? You remember we had this discussion about the ideal combustion? Yeah. So that's the reason we have the inlet diffusers, mainly with deceleration, right? But the thing you brought up makes sense as well. But the thing is, those fuels have to burn anyway. They're gonna stay in this huge afterburner process. So yeah, and then you have the fuel spray ring, which are going to add fuel, inject fuel to your system, right? That's the idea, to your air. Afterwards, you get to the flame holder rings, which essentially do exactly as the name suggests. They are supposed to help hold the flame. They increase the mixing, they increase the efficiency of the combustion in general, right? And then you have the afterburner exit, which is the inlet of your nozzle. Well, we have two things on the side. You usually have two things on the side. These dashed lines are there to keep the main body of the turbojet away from the explosion and this huge rise in temperature, like to keep it cool, to keep that body as cool as possible. Also, in the afterburner, you're gonna have huge screeching noise, right? So these liners act as an acoustic system that reduces the screeching noise that you're going to hear in an afterburner. The afterburner, as far as the jet is concerned, all of the jet, if you put the control volume on the jet, the afterburner can be assumed an adiabatic duct with insulated walls, meaning that there is no heat input from the walls of the control volume, right? And the parameters we need to analyze, we need to include in an afterburner analysis is one, is the heating value, which is the ideal heating value of the afterburner fuel, right? The amount of fuel flow rate or the exit temperature, and keep in mind that the tau lambda, we need to define a new tau lambda when we have the afterburner. So this is going to be tau lambda dash afterburner. Okay? T7 over T0, right? We also have the afterburner efficiency, which follows the same idea as the combustor efficiency. So your actual heating value divided by your ideal heating value, and the afterburner pressure ratio. Okay. Your new TS diagram is gonna look like this. Okay. So you start from station 0, then the compression stage, right? Go to the 3, then you have the combustor. Then you're gonna have a huge expansion in the turbine stage. Then you're gonna go over another combustion stage. You're gonna get to T3, right? That's for the TS diagram. Then you will go to another expansion process. And then you'll get to the exhaust. Is there any questions so far? No? Just have to keep in mind that the pressure ratio when the afterburner is off is always larger than the pressure ratio when the afterburner is on. That's the pressure ratio inside the afterburner chamber. And your power balance, if you will, is going to be changing. Your energy balance is going to be changing as well. When writing the energy balance, you have to include the afterburner in your analysis. So you're going to have m dot naught plus m dot f plus m dot f of afterburner multiplied by the enthalpy at stage 7, which is the exit of your afterburner, minus m dot f plus m dot f HT5, this is the energy balance for the afterburner. We can divide everything by m dot naught to get the fuel to air ratio of the afterburner and the fuel to air ratio of the combustor. Rearrange this equation to have an equation for the fuel to air ratio of the afterburner as a function of your fuel to air ratio, temperatures at the exit and the inlet of the afterburner, the heating value, the efficiency, and the CP. Okay. Just have to keep in mind that the CP of afterburner is let's actually continue this discussion in the next class because I'm exhausted. Huh? Yeah, I actually, whenever I feel like it's too much for the class, I look at Joshua's face. And he is going to sleep.